Okay, great. So I'm very excited to be here. Thanks to the organizers for the invitation. I will do my best to keep you guys entertained and do a little bit of informing. So I'm going to be giving 2 lectures on privacy, and my my basic plan is that I'm going to try to talk about what I would call sort of the 4 big ideas in modern privacy research. And sort of and ideally, I will give you kind of one example of each of the big ideas, and then kind of tell you where the current state of the art is at a very, very high level. And I'm happy at the end of this lectures. I'm hoping to have a sort of a PDF outline with a bunch of references in it. If you are curious about doing more, I'm happy to share that with anyone. So, but the sort of 4 big ideas that I'd like to cover in the next 2 lectures are going to be the following 4. So I'll give them names, and then I'll talk about what exactly each of these means. And each lecture, I'm going to try to talk about exactly 2 of these. All right, and optimality. So, can everyone read my handwriting okay? Can those in the back see it? Everybody's good? Okay. Yeah, so today so the 4 main ideas are going to be composition, amplification, stability, and optimality. And now what I mean by each of these, and these are the 2 that I'm going to talk about today. What I mean by composition is if you compute a private statistic or something privately, and you compute multiple private statistics, then you sort of still maintain privacy, or at least the degradation in kind of information you leak is graceful. Nothing explodes, suddenly you've leaked all the information. And amplification, which we'll talk about a little bit more as well, is sort of, are there natural techniques that exist that are things we would usually do in statistics that sort of increase the amount of privacy that we can provide in our estimation schemes? And so these are going to be the 2 big ideas for today, and this will be on Wednesday. Okay, so just to sort of set, good. All right, so just to set notation for what we're going to do, and hopefully, if the notation ever gets confusing, please stop me and ask questions. So we're going to assume we have data, and this will be sort of our standing assumption of the form xi, I equals 1 through n, and we will always represent our samples. So we have a sample of size n. We will always represent our samples as just their empirical distribution. So Pn, I will write as 1 on n, sum I equals 1 to n, and then I'll just write 1xi. So what I mean by this is that Pn is the empirical measure with point masses on each of our individual observations, and then this belongs to the class of all distributions on n points. Okay? So script Pm is going to be distributions on n points, and this is just the empirical measure of a sample. Everybody cool with this? Okay, so we have this, and we wish to compute some statistic or some estimator, which I will denote by theta of Pn in some parameter space big theta. So this is, we want to compute some estimation, say either like a sample mean, the minimizer of some loss or something like this, but some statistic that belongs to a parameter space theta. And now the entire game in privacy is that we have a randomized function, or the word we will use is a mechanism. Mechanism, which is just some random mapping from the space of probability distributions or empirical distributions into our parameter space. And we say this is what's called epsilon delta differentially private. If the probability that m applied to a sample Pn belongs to a set A is less than or equal to e to the epsilon times the probability that m of Pn prime is in A plus delta. Okay, and this is true for all, and I apologize, I'm going to run out of space here, but we'll leave this, for all neighboring distributions Pn and Pn prime. And so what I mean by this, okay, so this is the definition of differential privacy that we will use for all of today. and Wednesday. And so this is the sort of standard definition. So what this means is that my mechanism applied to one sample, the probability it belongs to a given set A, any set A, is upper bounded by e to the epsilon, so that's a small perturbation, times the probability that the mechanism applied to Pn prime, where Pn prime is just Pn, except I have replaced one observation. So by neighboring, I mean I have taken one observation from Pn and replaced it with some other observation. All right? And then this probability is bounded by e to the epsilon times this probability plus this little additive error delta. So this is the definition of differential privacy. This is sort of the standard definition in all of the literature, and it's what we're going to use today. Any questions on that?
How does it translate into anything? I mean,
How does it translate into anything?
No, how is it,
Yeah, good question.
make it private?
Yeah, so what does this mean in terms, oopsie. Sorry, I'm still learning how to use the boards. Okay, all right, so this is a very good question. So in the sort of, okay. Hopefully this will stay up this time. All right, so in the notation with which we are probably a little more familiar, there are many interpretations of this. There are Bayesian interpretations of this. There are interpretations of the definition via hypothesis testing. I'll give you the one via hypothesis testing. So an equivalent definition to differential privacy is the following. So consider consider an adversary out there. This is your hacker or whoever's trying to break privacy. So an adversary wants to test a null hypothesis versus an alternative, which is that the null is that the data is Pn is your sample, and the alternative, H1, is that Pn prime is the sample, where the Hamming distance, that is to say, Pn and Pn prime is less than or equal to, well, just is equal to 1. Okay, so I have changed one observation between Pn and Pn prime. An adversary knows all of the data except for the last observation and wants to test if that last observation belongs to Pn or Pn prime. So this is our hypothesis test. And differential privacy, an equivalent definition of this that I will not prove this is equivalent, we can formulate it as a necessary lower bound on type 1 and type 2 error, okay? So we define the type 1 error, and I apologize for the indexing, but we'll just use this. Type 1 error is alpha 0 equals the probability under H0. So that's my probability under the null that that the adversary can reject H0, and alpha 1 is the probability under the alternative that the adversary rejects H1. Okay? So this is the summed probability. These are the type 1 and type 2 errors. And differential privacy is equivalent to stating that dp, if and only if, let me make sure I get this right, alpha 0 plus a minor upward perturbation is greater than 1 minus delta, and alpha 1 plus a minor upward perturbation of the type 1 error, or type, is greater than 1 minus delta. Okay, so the summed probabilities of error in a hypothesis test with a little upward bump in terms of my allowed probabilities are basically near my probability of making a mistake, the summed type 1 and type 2 errors has to be nearly 100%. Okay, with a slight, where I have a little bit of a forgiveness for that I'm allowed here. So this is an equivalent definition of differential privacy. Does that answer the question? Kind of. Yeah.
So here, is this a simple or a composite alternative?
This is a simple. This is a simple test. Literally, I know that Pn. This is a particular sample, x1 through xn. This is an alternative sample, x1 prime through xn prime. So I know exactly what the two samples are. So this adversary is extremely powerful. The adversary knows everything except for the last observation in your data set.
But this mechanism should work for any Pn prime, but
So the key here is, sorry, I should have defined this. Neighboring Pn prime means that the Hamming distance, or the Hamming distance between these is exactly 1.
yeah, right. So this n doesn't depend on Pn
I'm not sure I understand the question. I apologize. Sorry, the question.
When I like construct a mechanism M,
Yes.
I don't construct a mechanism which only protects against a specific Pn prime in advance.
Right.
It should hold for all Pn prime.
Right, sorry. So the question is, okay, so but this mechanism is a randomized mapping from distributions or from samples, really, into my parameter space. Right, the mechanism has to be private for all Pn and Pn prime. What differential privacy is equivalent to is saying that for any pair of samples, that differ in only one example, then if an adversary who knows these two samples and gets the output of my mechanism. So the adversary gets to observe, so the adversary observes the output, I should have been clearer, M. So it observes the output of my mechanism, and then no matter what the two samples were, even if the adversary knew them ahead of time, the adversary cannot test, or at least can't test with high accuracy, whether the data was Pn or Pn prime. So a simple hypothesis test. You cannot solve this with very high accuracy, unless, of course, epsilon is very large or something like that. Okay, so this is the sort of testing-based definition. These are equivalent. Okay. Yeah, Philippe?
I think that the confusion comes from the fact that the adversary is so powerful that it even knows that if it was not Pn, it would know exactly what is the missing sample in Pn prime, right?
Yes.
And so I think the question is there anything to squeeze if you don't allow your adversary to know this, right?
Yeah, so that's a good question. So
I don't want to know what the other one is.
yeah, so the question is, what if your adversary isn't quite so powerful as this? Can you squeeze more out of the definition? Probably, but in 15 years or 20 years since the definition of this, we haven't really been able to give a weaker adversary and still provide any reasonable downstream consequences. We've tried and tried and tried, and it turns out many of the things that we want privacy to satisfy break. Like if you have a little bit of a weaker adversary, often what happens is you do two private mechanisms in a row, and then all of a sudden you compromise all the data or something like this. So we haven't been able to really weaken this in a very nice way yet. And I think people are starting to just say, you know what, we're going to punt on any weakenings, because we've not had success doing that yet.
Can I ask you one more question? I mean, it seems very counterintuitive for me, because in your first definition, it is more private if epsilon is small, but this definition requires epsilon to be large.
Well, sorry, the first, right, so more privacy is epsilon small, which is the same here. So if I say epsilon was 0, this says that the summed type 1 and type 2 errors are at least 1 minus delta. You should think of delta being nearly 0. So if I had a hypothesis test where type 1 error plus type 2 error is 1, then the best test is random coin flips. Just guess, right? So these are just literally the same thing. Okay, let me give a few of the sort of standard basic mechanisms, and then we'll start to talk about how we think about actually applying these. Okay, so the basic mechanisms that people use, these are sort of the two standard mechanisms. Let me see it. Let me see how I want to write this. Okay, let's define what's called the global sensitivity of my function is going to be the supremum over all neighboring Pn and Pn prime of the difference between theta of Pn and Pn prime. Okay, so I mean, you could also think of this as the Lipschitz constant of your statistic of interest. All right, but in the differential privacy literature, we call these sensitivities for reasons that are not completely clear to me. I think perhaps the word Lipschitz was scary. So we don't use Lipschitz, we use global sensitivity. So this is the global sensitivity. So for example, if my data xi are in between -1 and 1, and my statistic of interest, theta of Pn, is just the sample mean, sum I equals 1 to n xi, then the global sensitivity is exactly 2 over m. Because I could take a sample, put one observation at -1, one observation at +1, and that changes the sample mean by at most 2 over n. Okay? So then the Laplace mechanism just says that your mechanism is m of Pn is your statistic, theta of Pn, plus the global sensitivity divided by epsilon times a Laplace random variable whose scale is exactly 1, right? So remember that a Laplace, W is distributed as Laplace if it has density P of W equals 1/2 x above minus absolute value of W. Okay, so this is intuitive. I just add noise commensurate with how sensitive my statistic is, right? And so, for example, in the case of the sample mean, then the standard deviation of the noise I'm adding scales as 1/n. All right, sort of intuitive, right? Then the sort of slightly different mechanism, which is, oh, and sorry, this is epsilon 0, so delta is 0, differentially private. Okay, the second standard mechanism applies a little more nicely when we look at sort of Euclidean type spaces, and that's just to add Gaussian noise. All right, so you add Gaussian noise with a sufficiently large variance, and then you can get similar things. So let's let GS with respect to the 2 norm be equal to the supremum over all Pn and Pn prime neighboring of the 2 norm of theta of Pn minus theta of Pn prime. So that's the Euclidean distance between these. And I should say that these are always neighboring samples. So it's how much can I change my statistic or my optimization parameter or whatever by changing one example. Then the Gaussian mechanism which is defined to be m of Pn is my statistic plus Gaussian noise with mean 0 and variance, global sensitivity. Let me make sure I get this right. Sorry. I'm going to give myself a tiny bit more space. This is my statistic plus Gaussian noise with mean 0 and variance. Turns out you need 5/4 times the global sensitivity squared divided by epsilon squared times log 1 on delta times the identity. This is epsilon delta differentially private. Okay, so I add Gaussian noise, whose variance scales as the square of this sensitivity. So if I think again about the sample mean, I'm adding Gaussian noise whose variance scales as 1/n squared, because that hides the change of any one individual observation. All right, and so this follows, and I'm not going to do the calculation because, the probability that W0 belongs to A is less than or equal to e to the epsilon probability that W1 belongs to A plus delta whenever Wi is normal mu I sigma squared identity, and the difference between mu 0 and mu 1, 2 norm squared, times 5 on 4 log 1 on delta is less than or equal to sigma squared. Okay, there's just a comparison inequality for Gaussians, which you can kind of think of, if I were given 2 Gaussians, whose means are sort of close enough, my probability of being able to distinguish them or test between them is going to be very small, so long as the means are close enough together. Okay, so these are sort of the standard 2 mechanisms that people often use, is you sort of add noise commensurate with how sensitive your statistic is to changes in the underlying sample. As long as you add noise that can hide the amount of change, then you're going to be fine. Seems sensible. Okay.
The first example is a one-dimensional case, the second example is a multiple.
Right. So this is a one-dimensional case. This is for any dimension that you want. That's right. Yeah. I mean, of course, much of modern research in differential privacy is trying to understand what happens in high-dimensional cases. It turns out that the definitions of differential privacy often make doing high-dimensional statistics and things like that very challenging, and that's where a lot of the open questions currently are. Okay, any questions on that guy? Yeah?
John, is that boundedness or like quasi-boundedness like very necessary for DP in general?
No, it is, so that's a good question. So the question was, is this kind of boundedness, that my statistic doesn't change much with the underlying distribution, is that completely necessary for DP? It's not quite necessary for DP, for privacy, but it's close to necessary for privacy. And we'll talk, if time permitting, we'll talk a little bit about how that comes to play.
Even with that definition, the more separated your distribution are, the less, you will be able to do that, right?
Mm-hmm. Yeah, so the question is, what if this sensitivity is infinite? Can you still do anything? And the answer is, at least with these naive mechanisms, no. But we'll talk, as we get on farther, we'll talk a little bit more, and especially in lecture 2, when we talk about sensitivity and stability, we'll talk about how to deal with the fact that sometimes, often you have statistics that, you want to estimate a mean. Of course, one observation of an arbitrary mean can change the whole statistic arbitrarily. So how do we address this? We'll talk about that. That's a good question, and it's important, and we're still working on it. Okay. All right, so with those two sort of motivating mechanisms, oh, sorry, one last question.
So, in your definition of differential privacy, you require a lower bounds on errors, type 1, type 2.
Yeah.
But it seems you don't tell anything about what do you want from your mechanism, so what information you want to preserve.
Right.
You can take some completely random ones.
Yeah, so the question is, so the question was, the definition of differential privacy, we defined it as type 1, type 2 error, or somehow essentially a likelihood ratio bound on the distributions of my mechanisms. But I said nothing about accuracy. That's right. I said nothing about accuracy. So the following mechanism is always differentially private, return 0, right? That's a very private mechanism. It also communicates very little information. And so, of course, there's a trade-off between privacy and accuracy or things like this. And again, a lot of differential privacy research is understanding exactly how far you can get in terms of estimation accuracy while satisfying this definition. And we'll talk about that again when we talk about optimality. Okay, but no, you don't want any accuracy in the definition. The definition is purely a protection. Can I guarantee protection? Okay. All right. So with this sort of, I understand this is fast background. I have 2 hours to lecture, so we're just rolling through. So let me talk about the first of my kind of big ideas that we wanted to talk about, which is composition. And this is one of the first properties that you would want to get out of a privacy definition. And basically, the game is the following. Okay, so suppose you have mechanisms kind of in sequence, and we'll say we have M1, which takes your input distribution and spits out theta. But then let's say we have a mechanism M2. Let's actually have it go into theta 1. M2 takes in an empirical distribution, but it also takes in, say, the output of mechanism 1 and acts on that. And so it's going to output something in theta 2 and ... And finally, we have MK, which takes in your input sample distribution and the outputs of every past mechanism and spits out some quantity. Okay? So what's going to happen is I'm going to apply these in series. I do one private data analysis, then I do another private data analysis on the same data, do a third one, do a fourth one, all the way down. Okay? And what you would like to have, what you would not like to have, is that at some point in this chain, everything collapses and you lose all privacy. Right? And this, you actually see this in the real world. This happens a lot. So for example, suppose that, and here's an example of something that happened. Suppose that I have one data set which tells me that the times that, let's say I have one data set which is movies that were rented from a particular movie store and the times at which they were rented. And then I have another data set which is purchases individuals made with their credit cards and the times and places where they made those purchases, right? Okay, so now if I combine these two data sets, I can figure out who rented movies and what time and what movies they exactly rented. And this actually was a real thing. So Netflix at some point had prizes for predicting movie ratings as well as possible. And they had 2 prizes. The second one actually they had to take down because a woman was outed as having watched movies about lesbianism and she did not want to come out of the closet. And so this was bad. Anyway, so So that's often in the real world you see these things where you can, if you take two databases and combine them, you can find out a lot about individuals. And so we want to prevent that. We want this degradation in privacy to be graceful. Okay, and so now the question is, if I define the composition, and we'll define just for so M1 composed with M2 of Pn, I will call this to be equal to M1 applied to Pn, the pair, and M2 applied to Pn and the output of M1. So that's the composition of two mechanisms, and then proceeding inductively, we define the k-fold composition is M1 composed with M2 composed with ... composed with Mk private. Okay, so if I apply k mechanisms in sequence and release all the outputs of them, and they're allowed to depend on one another, is this still private? All right, so that's the question. And this is because, and once you have this, then this allows you to build sort of sophisticated mechanisms that do sequences of private operations and still maintain privacy. All right, and so the answer is yes. And here's the theorem. And it is that k-fold composition of epsilon delta differentially private mechanisms is, it's two flavors of private. It is both k epsilon and k delta private. And it is also, and I'm going to get the constants wrong here, but that's okay, epsilon times e to the epsilon minus 1, make sure I get this right, times k plus order 1 square root of k epsilon squared log 1 on delta and k delta differentially private. Okay, so you have, so you get two flavors of privacy guarantees by composing k of these together. And the first of them is you just add up the privacy parameters. So remember, we're thinking of epsilon being something like 1-ish is kind of the standard setting. But the point is that when we compose k of these together, you get roughly either k times epsilon, so a degradation of a factor of k in the privacy protections you're giving, or something like k times epsilon squared if epsilon is less than 1. Yeah, Rui. Oh, yeah, sorry. Differentially private. Okay. So this gives us this degradation. And now, and it turns out that this is well, I'll give you an example application of this idea, and this ends up being a very powerful idea. Okay. All right. So any questions? Let me give a proof sketch of one version of these things, just to kind of give a flavor of how we actually do this. But so, so proof sketch, to sort of understand roughly where this is coming from, is I'm going to focus on just the delta equals 0 case. Because dealing with the case where delta is positive is going to be kind of annoying. And here's the main lemma. It is that if m of Pn and m of Pn prime have densities, so if I just, we can think of these as densities with respect to some base measure, it doesn't really matter, have densities q0 and q1, and their log likelihood ratio, q0 on q1. So if L is equal to the log likelihood ratio between these, then if this log likelihood ratio is bounded by epsilon with probability at least 1 minus delta. Okay, so long as when I, this is under q0. So as long as when I draw an output under q0, that is to say an output of the mechanism Pn, as long as the log likelihood ratio here is bounded by epsilon, so I get relatively little evidence telling me that the data was either from 0 or 1, then the probability that m of Pn belongs to A is always less than or equal to e to the epsilon probability m of Pn prime is in A plus delta. Okay, so as long as my likelihood ratios are typically bounded, then I am guaranteed epsilon delta differential privacy. Okay, and the proof of this is just a little exercise. Excuse me. There's nothing super sophisticated about it, but if I just integrate the indicator of the set A under Q0, this is equal to, making sure I get this right, the indicator of A, indicator that L, my likelihood is less than epsilon, Q0, plus the integral of the indicator A, indicator that L is bigger than epsilon under Q0. But of course, we already said that this is less than delta, right? So this term is less than delta. And here I know my log likelihood ratio between Q0 and Q1 is bounded by epsilon. And so this whole thing is now less than or equal to e to the epsilon integral indicator A under Q1 plus delta, which is exactly the result that I wanted to show. Okay, so if I can, so if I think about the likelihood ratio between my two distributions, thinking of this as like a hypothesis test between two densities, as long as this log likelihood ratio or likelihood ratio is typically bounded, then I'm going to have a hard time distinguishing did the data come from Pn or Pn prime. Yeah? Okay. Sorry, I'm trying to learn how to use these things. Okay. All right. So how can we change this into a guarantee that we have a minor degradation in privacy when we do lots and lots of private mechanisms in a row? Let's just define the privacy loss random variable by, excuse me, Li is equal to log Q, let me make sure I get this right, Qi of theta I given Pn and theta 1 to I minus 1 divided by Qi of theta I given Pn prime and theta 1 to I minus 1. Where here theta I is equal to the output of the mechanism on Pn or Pn prime. Sorry. So theta I is the output of the IF mechanism, and Qi is the density of the IF mechanism. Okay, so now I'm just looking at a sequence of log likelihood ratios. Everybody okay with this? So I have the log likelihood ratio where I'm trying to test is the IF parameter that I output from the mechanism applied to Pn or Pn prime. Okay, but we know, we've sort of assumed that these are epsilon differentially private, right? So then what do we observe? Then clearly we have that the magnitude of Li is always less than epsilon by assumption. And and just note that in general, excuse me, if for any two distributions I have that, the absolute value of the ratio log P on Q is less than epsilon, then I have that the KL divergence between P and Q is equal to integral P log P on Q is less than integral P minus Q log P on Q. And this in turn is less than integral absolute value of P minus Q, absolute value of log P on Q is less than or equal to, so if these are bounded by e to the epsilon, this is bounded by e to the epsilon minus 1. So integral P times e to the epsilon minus 1 times epsilon equals to epsilon e to the epsilon minus 1. Okay, so if I have any two distributions whose log likelihood ratio is bounded, then their KL divergence is bounded by that likelihood ratio bound times e to the epsilon minus 1. All right, and so in particular, the expectation of the IF likelihood ratio given Pn and all my observations, theta 1 through, theta I minus 1 up to that point, what is this equal to? what's the expectation of a log likelihood ratio? It's literally the KL divergence, right? Because that's how we define this. And so this is equal to, this is always less than or equal to epsilon e to the epsilon minus 1. Okay. So now I have a sequence of random variables. Their expectations are bounded. The random variables themselves are bounded. Anytime you have a sequence of bounded random variables with bounded expectations, you apply what inequality? I feel like, sorry, I'm treating you guys like students, but Sven, what inequality should I apply now? Very close, but I have a martingale. Bounded dip, sure, whatever. Zuma-Hofting, yes. All right, thank you guys. I appreciate the call and response is nice. It is, right? I just finished teaching like 40, I was doing double teaching this year, so I'm still in like teaching mode, I apologize. Okay, so anyway, so we apply a Zuma-Hofting. And we see that the sum from I equals 1 to k of these likelihood ratios is always bounded by k times epsilon e to the epsilon minus 1 plus some numerical constant times square root of k epsilon squared log 1 on delta, with probability at least 1 minus delta. All right. And so this is, this is the sum of my log likelihood ratios. Now we just apply this lemma up here, which says if our log likelihood ratios are bounded, then we have differential privacy. This is the bound on our likelihood ratios. Okay, so that's it. So now you apply the lemma. Okay. All right. So any questions on that? It's a little sketchy. Yeah.
What's the size of this constant for the privacy mechanisms?
This order 1 constant right there? Or which constant?
The likelihood ratio constant.
Oh, epsilon?
Yeah.
So what is epsilon? So that's a good question. So the question is, what is epsilon? So it turns out that when they defined differential privacy, they had this great insight, which is that epsilon is always a small number, so you should use it in your definition, right? So in practice, okay, so the answer to this is that it's complicated. In practice, when you have a full system, say for doing a sophisticated statistical task, epsilon ends up, at the end of the day, when you finish your analysis, epsilon is typically something like 4 or 8. Okay, now hold on, I'm not done yet. But yeah, so if you were to blindly apply that in here, that makes no sense. We agree that all of a sudden now any guarantees you have exploded because you have, your likelihood ratio bound is like k times e to the 8, which tells me nothing. But what we will do is we will develop techniques that allow us to take a sort of nominal epsilon of like 1 or 2 or 4 and actually effectively shrink it to something very small, and then we will combine them. I'll give you kind of a full path as we go on at the end of this lecture, hopefully.
Is it possible to say for the differential privacy mechanisms you described before, for the Laplace and the arbitrary
Yeah.
mechanisms, some simple examples like mean estimation, what would be this typical size of this constant epsilon?
Yeah, so the question is, what about for mean estimation? What should we think of? So if I think about the Laplace mechanism all the way up there, so the sensitivity of my statistic is 1 on n. It's the sample mean, it's basically 1 on n. So if I think of epsilon being something like 1 on square root n, then I'm basically adding noise commensurate to the kind of inherent variance in the problem. And so then, like in very simple tasks, we can think of epsilon scaling as 1 on root n in the nicest case for very simple things like mean estimation.
The density of the random variables themselves, because it's Q0 and Q1 are
Oh, Q0 and Q1 are just the densities of my mechanism, whatever mechanism I happen to be using. Sorry.
So there's not the density, it would be just
Like the Laplace. It would just be the Laplace density. Yeah. Yeah. Those are properties of the mechanism. It has nothing, you can't have anything to do with the underlying sample because sort of we're working in this adversarial world where the adversary gets to choose what your underlying sample is in order to break privacy. Okay. All right. So just a quick remark. So I did this for the delta equals 0 case. If you have this kind of positive probability delta allowed over here, you can do a slight modification of these densities so that this likelihood ratio bound holds essentially almost everywhere and then go through the same argument, but it's just a bit tedious and you have to actually trace a lot of constants. It gets quite annoying. Okay, so this is sort of the big picture on composition. Right now it's sort of this abstract thing, but at least we've demonstrated, here is, in a sort of sketchy way, that if you do private mechanisms one after another, we have somehow a graceful degradation. You don't have this point where suddenly you have lost all guarantees of any protections you started with. Okay. So let me talk about the second big idea over there, which was this idea of amplifying things. And then time permitting, I'll talk about how we combine this amplification idea with composition to actually build like a sophisticated algorithm. Okay? So basically the intuition here is that many algorithmic choices you might make are actually going to improve privacy. And that might be like via doing regularization in a typical estimation problem, or doing some kind of subsampling thing like a bootstrap or something like that. And it turns out that those actually have a big impact on the privacy of your mechanisms. And so let me give the sort of most compelling example of this, I think, is subsampling. Although there are many other versions of this in the literature now. Okay, so let's say I have a mechanism, and for right now, let's say that my mechanism takes, inputs in Pm and outputs things in theta. Okay, so it's going to take a sample of size m now. So m is smaller than n typically. All right, and now I define the subsampling mechanism. Excuse me. M star of Pn is equal to m of P sub s, where I'm going to do, what I'm going to choose is s is chosen from 1 through n, and its cardinality is exactly m, is chosen uniformly at random. Okay, so by this I mean, and I'm sorry, I should give a definition, and here Ps is equal to 1 on m times the sum over I in s of the point masses on xi. Okay, so I choose a random subsample of my original data, and I apply my mechanism on that random subsample. Now the question is, if this original mechanism was private, how private is this kind of more global mechanism that just chose a random sample at a sort of subsample at random and applied the original mechanism? All right, so if m is epsilon delta dp, then how private is this randomly subsampled mechanism m star? Okay, and then frankly, I think the somewhat amazing theorem is the following. So theorem, let's let q be the subsampling ratio, so q equals m over n. So this is the size of this, the ratio of the subsampled size to the full data set size that you took. Then m star is log 1 plus q e to the epsilon minus 1, make sure I get this right, q delta differentially private. Okay, so remark, if we think of epsilon being less than or equal to 1, then e to the epsilon minus 1 is about equal to epsilon, and then log 1 plus q e to the epsilon minus 1 is about equal to q epsilon. Okay, so whatever fraction of data you sampled out, you get sort of basically a linear kind of, I want to call this an increase, although it's making epsilon smaller, which is good. You get sort of a linear improvement in the amount of privacy you can provide by doing this random subsampling. Okay? Yeah, fine.
So epsilon, if epsilon is 0 and delta 0, everything stays 0, right?
If epsilon is 0, delta 0, everything stays 0.
Because I wanted to ask again about the definition, whether there's so that when you look at these likelihood ratios,
Yes.
it reminds you like of, okay, if the effective sample size or something like that is smaller,
Yeah.
the log likelihood ratios are going to be
Mm-hmm.
So if I just kind of say I take a sufficient statistic of data,
Yeah.
and then I form the sufficient statistic using a smaller sample size, is that also a way of making something private?
That is not enough to guarantee pure privacy. You still have to add a little bit of noise. Because if I just took if I took a random subsample, but the adversary knows, say I have a two-dimensional statistic or two-dimensional data, which is just two scalars. Then if I know, only one individual has a non-zero entry in the second component, even if you give me a subsample, I can just check is there any non-zero entry in the second component. So we still have to be a little bit careful. Okay, let me give a proof of this, and then I'm gonna be evil because I had planned for an hour lecture and we started 10 minutes late. So to give the full I would like to give a full example pipeline of applying both composition and subsampling to give a reasonable algorithm for solving stochastic optimization problems, okay, which will kind of get us to almost state of the art. So forgive me for going a little bit over the official timing. But okay, so let's give a quick proof of this. And again, we'll do it in a bit of a sketchy way. But let's say that Pn and Pn prime differ in index I. Okay, so they're only going to differ in index I. And then what we have is that the probability that I belongs to the random set S is exactly, equal to M on N is Q. Okay, so the probability I randomly choose the index in which they differ is exactly equal to Q. Yeah? Okay. Okay, so then if I think about if I think about the probability that my randomly subsampled mechanism outputs something in a set A, this is exactly equal to 1 minus Q times the probability that my original mechanism applied to a subsample S belongs to A, given that I did not choose that index I, right, plus the probability that my randomly subsampled mechanism belongs to A, given that I did choose the index I. Yeah? Okay, so this is, but the nice thing is that, this term right here, this first term, because the index I wasn't chosen, this is exactly the same as the mechanism applied to the alternative sample. Nothing changes, right? So this is also equal to the probability that M applied to the alternative sample belongs to A, given that I is not in S. Okay, so that didn't change. And so then we only have to deal with this term. All right? So if we consider the second term, we can get actually two clean upper bounds on this. Then certainly, if I change this to the alternative sample, then the change in the distribution is bounded by e to the epsilon, right, times the original thing. Then we have that the probability that M of PS belongs to A, given that I in S, is certainly less than or equal to e to the epsilon times the probability that the mechanism applied to the alternative sample belongs to A, given that I selected observation I plus delta. Okay, so we're good there. But this isn't quite enough to give us the theorem we wanted. What we're going to have to do is another little, sort of a little clever trick. Nothing too sophisticated, but we're going to also recognize that in this particular case, the difference between this and this term is also very small. Because I can just remove the ith index from this and replace it with something else. And that's only changing one example in my subsamples. And so these two are actually also very close together. So we also have that the probability that M of PS belongs to A, given I in my random subsample, is also less than or equal to e to the epsilon, the probability that M of PS belongs to A, given that I is not in the subsample, plus delta. Okay, and now this is a little bit of a funny inequality. So why does this hold? What you can think of this as is, for any subsample I choose, right, there's another subsample over here which is completely identical, except I removed the ith index. I swap out the ith index with something uniformly at random. But that's only changing one observation in this sample, and so then I know that the likelihood ratio is bounded by e to the epsilon plus delta. So I can always couple any pair of these and change one example, and I get this bound of e to the epsilon. Okay, so now I'm actually in business, and we can actually give the rest of our proof. Okay, so let's go ahead and do that. All right, so, excuse me. If I let P0 equal to the probability that M of PS belongs to A, given that I is not in S, and P1 equals P of M of PS is in A, given that I is in S, that I actually subsampled this thing, and P1 prime is similarly defined, except that I make this the alternative distribution, PS prime, then what do we know? Then we have that, excuse me, the probability that M star of Pn belongs to A is equal to 1 minus Q, let me make sure I get this right, times P0 plus Q times P1. And I have that, excuse me, if this is P, then P is always less than or equal to both 1 minus Q P0 plus Q times e to the epsilon P1 prime plus delta, and 1 minus Q P0 plus Q e to the epsilon P0 plus delta. And I have both of these. That's just these two inequalities right here. Okay, so I upper bounded P1 by e to the epsilon P1 prime, so that's the probability under my alternative, and e to the epsilon P0, where this is this original quantity. Okay, and now I'm just going to do a somewhat magical substitution. So then for any lambda in between 0 and 1, I can take a convex combination of these two inequalities, and that will still be an upper bound on my probability that my mechanism outputs something in A. All right, I get that P is less than or equal to 1 minus Q P0 plus, let me make sure I get this right, Q times the quantity, 1 minus lambda, we'll do this one first, e to the epsilon P0, then there's plus lambda, e to the epsilon P1 prime plus Q delta. Okay, and then I choose I'm not gonna go through the sort of algebraic boringness, but I can choose a particular lambda to get exactly the quantity I want, and then I just set lambda equals to Q plus 1 minus Q e to the minus epsilon. And what we get is that this becomes literally equal to 1 plus Q e to the epsilon minus 1, make sure I get this right, times 1 minus Q P0 plus 1 plus Q e to the epsilon minus 1 times P1 prime plus, Q times delta. And that is exactly, maybe I'll write the last step just to be absolutely complete. That is exactly equal to 1 plus Q e to the epsilon minus 1 times the probability that M star applied to Pn prime belongs to A plus Q delta. Okay, so it was a little bit of algebraic manipulations, but the point is that by doing a little tiny bit of subsampling, we can amplify the amount of privacy we have in a pretty substantial way by just choosing out random subsamples. Okay. So let me take 5 minutes. I'm gonna use my fully allotted time because well, I don't know. I think this application is kind of nice because it actually encapsulates both of these ideas into a sort of a full pipeline of a data analysis you might want to do. Okay, and so the application is going to be stochastic optimization. And this is one of the main applications of these ideas, and we can kind of combine everything together. And this is sort of one of the active areas of research now, is figuring out exactly how we solve stochastic optimization problems under privacy constraints. You know, if I'm Google, if I'm Apple, if I'm one of these large companies, I want to collect data, solve optimization problems on them, but protect privacy simultaneously. Okay, so I want to minimize ln of theta is equal to 1 on n, sum I equals 1 to n of the loss of theta on a data point xi, where L is m0 Lipschitz and grad L is m1 Lipschitz. Okay, so let's say my gradients are smooth, my gradients are Lipschitz continuous, and the loss itself is Lipschitz. Okay, and convex, sorry. Okay, then the most natural strategy for doing this is the only algorithm that anyone knows how to run anymore, which is stochastic gradient method, right? Yeah, the stochastic gradient experience is another name for it. So what we're going to do is run that and then try to understand what happens. Okay, so you just iterate the following. Let's see what we do. We draw a subsample of size m uniformly at random. And then we just update theta k plus 1 gets theta k minus some step size times the gradient of my loss evaluated on that sample plus Gaussian noise, okay? Plus WK. I'll call this my stochastic gradient, GK. And the Gaussian noise is going to be scaled so that this is a differentially private estimator of a sample mean. All right, which will give me, every step of this will be differentially private. All right, so I'm just going to erase things here so that we save time. Where WK is normal, 0, and the exact amount of randomness I'm going to have to add is the Lipschitz constant squared divided by the subsample size m squared times log 1 on delta by epsilon squared, and then the d by d identity matrix. Okay, so I'm adding noise that scales as the Lipschitz constant divided by the subsample size. Okay, so that means that each of these noise additions is exactly epsilon delta dp, yeah? So every stochastic gradient, every GK is epsilon delta dp. And if you go through your favorite analysis, you know, maybe you pick up one of Anatoly's papers, what you will find is there will be a convergence guarantee for this algorithm, right? And what it will say is that expectation of the loss after k steps of this algorithm minus the best loss is less than or equal to, excuse me, the Lipschitz constant of the gradient times the radius squared divided by k plus, excuse me, alpha times the variance of your gradients plus r squared on alpha k, where r squared is the radius theta 0 minus theta star 2 norm squared. All right. So we have this kind of a convergence guarantee. And then what we can immediately see is that we're going to have the following, and what is the variance of each GK is less than or equal to Lipschitz constant squared on m, because that is the variance of this gradient estimator, because we did a subsample of size m. And then this thing has variance exactly scaling as plus d times, what did we write? Sorry, where are we? m0 squared divided by m squared epsilon squared log 1 on delta. All right, and so now the question is, when can I get this to be basically the same as though I had done this without privacy? All right, so when do I get the same kind of convergence rate? And so the total privacy loss per iteration, and we're going to use our subsampling here, is basically about q epsilon q delta for q equals our subsampling rate. Right? So that is the subsampling theorem right here. That's applying this idea. So this is how much we lose in every step. And then so if we do k steps of this, well, now I can apply my main composition theorem here. So after k steps, our total privacy loss is about equal to k times q epsilon squared plus square root of k q epsilon comma kq delta. This is the total privacy loss. And excuse me. So long as we choose epsilon to be sort of reasonably small, or a subsampling rate to be small enough, then this is kind of negligible, is the whole idea. All right, so let me just substitute in some constants here. Where'd my eraser go? So let me make sure that we get this. So as long as epsilon squared is sort of bigger than something like the dimension divided by m, that's my subsampling rate, log 1 on delta, then this term dominates the variance. Then the variance of my subgradients is bounded by something like m0 squared on m, and we get our sort of final convergence rate. Choose my step size equals 2. So remember, we have our step sizes here. Choose my step size equal to radius divided by square root of k times, making sure I get this right, 1 on m0, and we get that the expected regret is less than something like m1 r squared on k plus m0 r divided by square root k m. Oops, sorry. All right, and the total privacy loss, sorry, so and so long as our subsampling rate is small enough, we get that the sort of total privacy loss, epsilon total, is equal to kind of k m on n epsilon squared plus square root k m on n epsilon is small. All right, I'm going to just leave it at that for now because I've gone a bit over. But big picture, what have we done in a sort of a quick and dirty way is said that, all right, if I'm willing to tolerate many iterations of this algorithm and using very, very small subsamples, so as long as m is quite small, I can actually maintain reasonable privacy at the end of the day. You know, as long as m is sort of, say, smaller than 1 on square root the number of iterations I'm taking, then I have very little privacy loss, and yet I still have reasonable convergence in terms of what we would expect in stochastic optimization. Okay? And so this is kind of one application of how you put everything together. And sort of nailing down exactly how to do this in the best ways is actually kind of where the research frontier is trying to get sort of this nailed very, very precisely and understand exactly how best to solve problems like this. Okay, with that, I'm going to stop. I'll take any questions. Thanks a lot for sticking around a little extra.